Okay, today we are going to go over how your nerves make electricity. And this should be a pretty good review of what we did back with muscles. Because if you remember, we've already talked about sodium on the outside, potassium on the inside, action potential, resting potential, polarization, depolarization, repolarization. So a lot of this will be a review. So if you actually have your notes on muscles, you could get those out and kind of follow along and just add to it. But if not, here we go. So we talked about how your cells naturally have a buildup of sodium on the outside and potassium on the inside, which leads us to this thing called potential. And you guys, sorry it's so wobbly because, I'm sitting here trying to record this. Well, when you talk about somebody's potential, it's what could they do? Well, your cells have something called a resting potential or a membrane potential. And basically what this means is, this is how much electricity that cell could make. But remember, not all cells make electricity. Your nerve cells have the ability to make electricity. Remember, your nerve cells are called neurons. And then your muscle cells also have the ability to make electricity. But all of your cells have what's called a resting or a membrane potential. And this is how much electricity that cell could make. Because if you remember, all cells have a charge due to the natural buildup of potassium on the inside of the cell, sorry about that, and sodium on the outside of the cell. And if you remember, potassium is the weaker of the two ions. So if you look at a diagram with the cell membrane, you'll usually see pluses on the outside, that represents the sodium, and you'll see negatives on the inside, and that represents the potassium. But every cell in your body has this buildup of charge. Okay? And again, since sodium is the stronger ion, it gives the outside of the membrane a positive charge, while the weaker potassium gives the inside a negative charge. And if you remember, that's what it meant to be polarized. So all of your cells are polarized. All of your cells have a strong charge on the outside of them, which is your sodium, and all of your cells have a weaker charge on the inside, which is potassium. So just like a magnet, which has a north pole and a south pole, your cell membranes have a north pole and a south pole. The outside is the north pole. It is the overall stronger charge, and the inside is the south pole. It's the overall weaker charge. So every cell in your body is polarized. Every cell in your body has this buildup of charge. So every cell in your body has the potential to create electricity. And so when we talk about resting potential, that's what we call this natural buildup. This natural buildup is called the resting potential because the cell is doing nothing, meaning it's not creating electricity. It's not moving sodium, potassium back and forth between the cell membrane. This is also called the membrane potential because that's how much electricity the membrane could make. Remember, potential is how much you could do something. And since we're talking about making electricity, this is the nervous system. This is how much electricity could that cell make. Every cell in your body has a resting potential. It's negative 70 millivolts. Every cell in your body is the same because every cell has sodium on the outside and every cell has potassium on the inside. So every cell has the same resting potential. Every cell has the same membrane potential. That's how much electricity you could make. But remember, your nerve cells are going to take these ions and swap them. Remember, we talked about how when they swap them, that's going to create electricity. And again, sorry that this is so shaky, but I'm having a hard time holding it still. Now, we also talked about this thing called threshold. Okay? And when we talk about threshold, it says each cell membrane has special gates. Okay? These are proteins in the cell membrane. Because potassium is positive and sodium is positive, you guys know like charges repel. So if sodium just tried to diffuse into the cell, the potassium would push it right back out. If potassium tried to diffuse out of the cell, the sodium would push it right back in because like charges repel. Well, you got to be able to move things back and forth. So you have special doors we talked about. These are integral proteins that we can open in order to let things go back and forth. So these special gates are called gated ion channels. Okay? Gated let you know that you can open and close it. Ions let you know that you're going to be moving anions or cations, which are positive ions or negative ions back and forth. They're also called voltage-gated channels. Again, gated lets you know that you can open and close them. Voltage lets you know this is going to have something to do with electricity. So if you remember, these integral proteins are proteins that go through the entire cell. And you can change their shape and you can make them into a tunnel. They're called channel proteins. Or they could be carrier proteins that allow you to carry things back and forth. So ions cannot diffuse across the membrane by themselves. Because like I said, like charges repel. So if sodium tried to come into the cell, the positive potassium would push it right back out. And if potassium tried to leave the cell, the positive sodium would push it right back in. So we're going to have these doors that we can open and close in order to let these guys to move back and forth. And you know that doors cannot open by themselves. So when we talk about this thing called a threshold, okay, right, these channels are proteins that have to change shape in order to make a tunnel that the ion can pass through. Okay? So they can't do this by themselves. A door does not open by itself. Okay? And you could argue, well, no, the wind blew it open. Okay? The door did not open by itself. And so something has to change the shape of these proteins. Something has to open these doors. And that's what it is when we talk about this thing called threshold. Okay? Threshold is the push needed to get the door open. Basically, what does it take to get that protein to change shape? What does it take to get that protein to allow things to go back and forth? And so depending on the type of nerve you have, different things have different thresholds. Think of it as a light switch. You have to turn that light switch on. That makes a connection so electricity can run from the cords in the wall up to the light. When you turn the switch off, you break that connection. And so with threshold, it's what does it take to turn something on? What does it take to get that nerve to make electricity? And so different neurons are categorized differently. For example, the rods and cones of your eyes are called photoreceptors. Photo meaning light, receptor means to receive. So they're going to work with light. And what actually happens is when the light goes into your eyes, it heats up these neurons. Remember, neurons are nerve cells. It heats up these neurons, and when they heat up enough, it's like flipping the light switch. Once they heat up enough, these proteins change shape, and these doors open, and sodium, potassium can move, and we're going to create electricity. You're hearing my voice right now. You have little hairs inside of your ear. Every hair in your body is attached to a nerve. If you pull on your hair, you can feel it. If you touch your eyelashes, okay, you can feel it. Every hair in your body is attached to a nerve. So you have little hairs deep inside of your ears. And right now, those little hairs are vibrating. And when they vibrate enough, they flip a switch in that nerve that it's attached to, and these doors open up, sodium, potassium can start swapping places, and they can make electricity. Your sense of smell is done by chemicals. You have to absorb enough chemical in order to flip the switch. That's why when you have a stuffy nose, you can't smell anything. It's because you can't absorb enough chemical to flip the switch. You have to reach threshold. So depending on what nerve we're talking about, threshold will be different. But something has to open these doors. Remember, these doors are called gated ion channels. They're proteins. You basically have to change their shape. And once they change shape, it's like opening a door, and now sodium and potassium can swap back and forth. And so we talked about this thing called action potential. Resting potential is the same thing as membrane potential. Resting potential and membrane potential, this is how much electricity the cell could make. If you are in action, you're actually doing something. So action potential is how much electricity the cell actually makes. And so if you remember, it has to do with the swapping of the sodium potassium. So, sorry, just the way the color is on this. So remember, when the cell is doing nothing, it's in the resting state. So potassium is inside and sodium is outside. So we talk about how the cell, let me get this a little bit closer. The cell is polarized, which means it is normal. It's normal to have sodium outside. It's normal to have potassium inside. So it's positive on the outside. We say it's negative on the inside because it's weaker. So the cell is doing nothing. Well then, if threshold is reached, okay, so in the case of your ears, the hairs vibrate enough. In the case of your eyes, the nerves heat up enough. Okay? But when threshold is reached, you change the shape of the protein. You open the gate. So that's what we talked about, the gated ion channel, the voltage gated channel. You open the gate. So basically you open the door, and if you remember, that allows sodium to go in and potassium to go out. Remember, sodium's a bully, so it rushes in and it picks up potassium and it throws it outside. And so when it does that, it creates electricity. Well, this is what we call depolarization, because now it's opposite of what it's supposed to be. Sodium is supposed to be outside and potassium is supposed to be inside. Now it's opposite. So that's what we call depolarization. And if you remember, when they pass by each other, they create electricity. Now, something we did not talk about with muscles, okay? Oops, sorry. Okay. And so this causes a chain reaction. Okay. So now we're actually creating electricity. And when we create electricity, remember, that's what's called the action potential. That's the same thing as an impulse. So we talk about the nerve impulse. We're talking about those cells are making electricity. They're actually doing something. So that's the action potential. Remember, the resting potential is when the cell's doing nothing. It's also called the membrane potential. This is how much electricity it could make. The action potential is how much electricity it's actually making. Now, remember, your body wants to be better safe than sorry. So it only takes one sodium to push out one potassium. But your cell will actually do what's called hyperpolarization. Okay. Only a small amount of sodium is needed to cause the action potential. But better safe than sorry, your body will put a bunch of sodium into that cell in order to make sure that you push potassium out. And so we kind of overdo it, but we need to make sure that we create electricity. We need enough gasoline to get that fire started. Okay? So your body is going to overcompensate a little bit. It's going to allow in a lot more sodium than you need to, just to make sure that the potassium comes out and you start creating the electricity that you need. And we talked about how, remember, the cell doesn't like to be this way. The cell does not like to be depolarized. It does not want potassium outside. It does not want sodium inside. So it's going to try to switch back as soon as possible. And this switching back, if you remember, is called repolarization. And so we have this thing called the sodium-potassium pump. Okay. The sodium-potassium pump's job is basically to put everything back to normal. It will pump the sodium back outside of the cell. It'll put the potassium back into the cell. So remember, when the cell's doing nothing, we say it's polarized. When the cell is swapping, when the sodium and potassium are swapping places, it's depolarized. And when your body is putting everything back to normal, that's what it means to be repolarized. And we talked about how the time it takes for this to happen is called the refractory period. That's how much time it takes to go from polarized to depolarized back to being repolarized. And we're talking about less than 1/1,000,000th of a second, if you remember correctly. So here is kind of what happens. So remember, this is your neuron. These guys, if you remember, are called dendrites. They're the ones that collect the information and they send it to the nucleus. And the nucleus figures out what's important and what's not, and then it sends the information down the axon. And then we have our little boutons down here that we've talked about before. So this represents the neuron. The positives represent the sodium. The negatives represent the potassium. And so this yellow section is what's considered to be normal. So that's polarized. Well, here a door has opened and the sodium and potassium have swapped places. So here you can see sodium is now inside of the cell. That's what it means to be depolarized. That's going to create a spark of electricity, if you remember, which will open this door. Then the swap takes place. That creates a spark of electricity, which opens the next door. So you can see how the blue represents the depolarization. You can see how the blue starts to move down the cell. So this door opened, made electricity, which opened that door, which made electricity, which opens that door. Well, remember, As soon as it's depolarized, it wants to repolarize. So here it's depolarizing. You can see that sodium is coming in. Here I'm going to repolarize. Okay, I'm going to take that potassium and try and put it back inside. And so then here I am back to being polarized. Okay. Polarized, if you remember, I'm going to have the sodium on the outside, potassium on the inside. So depolarization is the blue, repolarization is the red, and being normal, being polarized, is the yellow. Okay? Which is the same thing as your resting potential. And so you can see how the electricity, which is the blue, moves down. Because remember, this will open a door which creates an electrical spark, which opens the next door which creates the electrical spark, which opens the next door, and that creates an electrical spark. Right. And so, oops, what happens now? Well, you'll just have to wait until later.